Okay, today we're talking about exponential functions, and unlike stuff we've done in the past, whether x squared or x to the third, x is usually the base, and then there's an exponent above it, like squared or third, Here, the x is the exponent, so these are called exponential functions. It makes it tougher to use algebra on these problems because how do you solve for something that in the exponent? We'll learn how to do that this chapter. But first, we're going to start about this family of functions that when a is bigger than 1, they all have the same kind of look to them. I'm going to do the parent graph, which is, I would call 2 to the x, although you'll see 3 to the x and 4 to the x are very similar as well. So let's just plug in a few points for x and y and figure out what the graph looks like here. So I'm just going to start with like 0, 1, and 2 and see what happens when you plug those in. So this would be 2 to the 0 power, which is, hopefully you know, is 1. 0, 1. That's actually the point you have to memorize. So that's the main point of this graph. I know that sounds funny, but on the parent graph, I only need you to memorize 1 point. 0, 1 is the point I need you to know. Plug in this one to the first. Well, that's just 2. 1 comma 2 is this point. See the y value doubled. 2 squared is 4. 2 comma 4. Again, the y value doubled. Now let's plug in 3. 3 squared equals 9. So 3, if you have a graph paper that big, 3, 9 would be right up here. Looks like it's going up pretty fast. It's doubling every time x increases by 1. Let's plug in some negatives and see what happens. So we get 2 to the negative 1 when we plug that in for x, which is actually the reciprocal that's 1 over 2, or 1/2. So negative 1 comma 1/2 is right about there-ish. Negative 2 would be 2 to the negative 2, which is 1 over 2 squared, which is 1/4. So it's even smaller there, right about, I don't know, there. Negative 3, you can see it's getting smaller and smaller here, but it's never actually going to touch 0. It's going to be 1 over some big number, 1 over 2 to the third, in this case, 1/8. So it's getting smaller and smaller and smaller. It's getting closer and closer to 0, but never quite touching. So it's approaching. This is not going straight up. It's going up and to the right forever. So it's not actually going straight up. Make sure that goes a little bit to the right there. And then there's going to be a thing called an asymptote here at, it's a horizontal asymptote, which the graph is approaching. You see only on the left, it's approaching the asymptote. The equation for the asymptote is y equals 0. You always have to label the asymptote with its equation. Horizontal line, so it's y equals, and the value there is 0. And so that's what you need to know. So if I asked you, hey, graph this, this is what I would expect. I don't expect you to graph every point perfect. This is what I would expect. Start with the asymptote. Y equals 0, asymptote. Plot that point 0, 1. Behavior to the left approaches the asymptote, hits that point, boogies on up really fast. That's the graph of 2 to the x. That's what I expect for a sketch. I don't expect every point perfect. I expect a sketch where, yeah, it's pretty good. What's the domain and range of this graph? So if you look at domain, you can plug in any x value. It goes left and right forever. So the domain is all reals, or negative infinity to infinity. And the range, though, is limited. It doesn't seem to go down here at all. It doesn't have any graph below the x-axis. So y seems to be actually always above, so greater than 0. It's not even actually equal to 0. That seems to be the asymptote. So y is greater than 0. It just helps you to understand, like we're talking more and more about domain and range, x's and y's, all the possible x's, x could be anything, and all the possible y's there. There's a second parent. So this parent function is when a is very small. So when a is like a fraction, like 1/2 or 1/4 or 2/3 or 5/8, anything between 0 and 1 for that value of a. We'll do the main one, which would be 1/2. So we're going to plug in some points here. And again, this is one I want you to memorize. And so let's just plug in some points to see what happens. 0, 1, 2, 3, negative 1, negative 2, negative 3. Okay, so if we plug in 1/2, so that's 1/2 to the power of 0. Well, anything to the 0 power is 1, unless it's 0. Okay, so 0, 1 is the main point in this graph as well. That's the point you need to memorize. It's the same point, by the way, but the behavior will be different on this one, I think. So let's see, 1/2 to the power of 1 is, well, 1/2. Ooh, so 1 comma 1/2 looks like it's getting smaller as x increases. So 1/2 to the second would be 1/2 times 1/2, which is 1/4. Fourth. So it's getting smaller there. This would be 1/2 to the third power, which is 1/8, which is even getting smaller. It's getting super small there. Okay, so let's plug in a negative. So 1/2 to the -1, that's a reciprocal, so it's going to be 2 over 1 or 2. So -1 comma 2, that's interesting. Okay, so 1/2 to the second -2, that'd be the reciprocal, so it'd be 2 to the squared, which is 4. Probably see what's happening. It seems almost like a reflection of the other graph over the y-axis. In fact, that is what it is. And so this graph, again, is going, so instead of growing, this graph is called exponential decay. So when the graph, let me erase that part of it. It should go up there. Oops. There we go, sorry. Okay, so the graph should approach the asymptote here, which of course is, don't forget to draw the asymptote and label it with an equation. This is y equals 0, it's the asymptote. And it has a little arrow on the end as it goes up and to the left forever. So this is exponential decay, this is exponential growth. So growth is, as x increases, it's growing, the y value is increasing. This one, as x increases, the y value is decreasing, so it's decaying there. Domain and range, well, we have the asymptote. Again, domain is all reals, and range is y greater than 0. So actually, the domain and range are the same. Okay, can you identify growth or decay? So if you look back at these two examples, when a is bigger than 1, it is growth. When a is smaller than 1, or between 0 and 1, it is decay. So that base of the exponent is what you're looking at. So here we're looking at the number 3. This is definitely going to be growth. So it's going to grow because that a value is bigger than 1. Don't look at the 2, it's the base of the exponent. So we're looking at the number inside of there. This one is going to decay. It's going to be getting smaller by 1/4 every time. Again, this is the number you're looking at here. It's going to grow, exponential growth. That's easy. Okay, exponential growth formula. So this is a formula for compound interest. Interest is compounded yearly. So if you put $10,000 in a CD, which is a bank product that they offer called a certificate of deposit, it earns 4% a year. Oh, that's really good. That's no bank's giving that right now. How much money will you have in 20 years? So what you're going to do, you need to know what these things stand for. So A is like amount there. So the A in there is amount. It's the name of the function. So the amount after t years, in this case, after 20 years. So t is time. This is amount, although it's the name of a function. So just keep that in mind. It's not like A times t, it's A of t. It's the amount after 20 years is how we read that. So it's not A times 20. It's like f of x, but A of 20. Equals, P stands for the principal. That's how much you invest, the principal. So this will be $10,000 times 1 plus R is the rate written as a decimal. So don't write 4 right here. You want to write 0.04, if that makes sense. And then T, again, is we already have that. It's the time. So to the 20th power. So at this point, you really just type that in your calculator. Okay, so 10 times 1 plus 0.04 to the power of 20. 21, wow, 21,000 911. Let's see if that's, you can mouse up and press enter and it shows you more digits. Oh, it does show you more digits. So that's actually that's 23 cents. So I like to round to the nearest cent. So if you mouse up and press enter, you can see the rest of that number. And so this is money, so it makes sense to round to the nearest penny. That's pretty good. If you're at 4%, I mean, you doubled your money in a little over double your money in 20 years. So not terrible. So let's try this problem. Ooh, this kind of interesting. How many years will it take to grow to at least 1,500? So 1,500. I want the value to be at least that. So I think I'm going to say it this way. I guess. Let's do the formula, which would be 1,000. I think that's P times 1 plus the rate, which is 0.02 as a decimal, to the power of T. Ooh, weird, isn't it? Okay, so we've got to try to solve this. So I'm going to divide by 1,000 here. So that's 1.5, okay, less or equal to, this cancels. That's in the parentheses 1.02 to the T power. How many years will it take to grow to that? So 1.02 to the what power will that be? So without knowing how to do logarithms, have we learned logarithms? I don't think we have. I guess we could guess and check this. Let's try. Okay, so this is it's going to be a much easier problem in just a day or two, but we're not quite there. So you will learn how to do this. 1.02 to the power of, let's say it's 10 years. I don't know. 1.21. I need it to be 1.5 or bigger. Let's make it 20 years. Oh, we're getting closer. I'm going to try 25 rather than 30. That's too much, right? So what's the first year? So let's just try 22. That's still too much. Maybe, we'll see. 21. To the power of 21. Oh, so 20 is not 1.02 to the 20th power is not enough. So it's a little over 20 years, between 20 and 21 years. So if I'm rounding it, I might just say 21. You need at least around 21 years approximately. We'll learn how to 21 years to solve this more exactly in just a few days. We're not there yet, but that's one way you can. That's a pretty tough little problem there, but that's one way to solve it. Okay, so let's look at transformation just for a minute. So maybe this will help us. So if you see here, this is our parent graph, right? This is y equals 2 to the x. I told you it goes through 0.01 as an asymptote. You can almost see it there at y equals 0, and it's growing, right? Watch the difference. When I click this, it's going to change the a value to 3. And I told you that when a is bigger than 1, the graph has a similar look. Well, watch what 3 looks like. Did you catch the difference? There's 2 to the x. There's 3 to the x. Almost the same graph. It goes through the same point, has the same asymptote. It just grows a little faster. 4 to the x, same thing, grows a little faster. 5 to the x, 6 to the x, 7, 8, 9. So it's growing a little faster each time, but the graph is the same. And since we're just sketching this, have you noticed we're just sketching? It's not really a graph with a lot of points. 2 to the x looks a lot like 3 to the x, which looks a lot like 4 to the x. As far as our sketching is concerned, they're basically identical as far as our sketch is concerned. So let's do this. So let's go, so 3 to the x of the parent graph has the asymptote at y equals 0. I'm just doing the parent graph first, and then we'll transform this. And this is going to be as a point here at 0, 1. And the parent graph has this, so I'm talking about 3 to the x here. It looks kind of like this, roughly. That's the parent graph. Now let's talk about transformations. So first, just remember how to do transformations from previous problems. So like this is, you don't have to write this down, but this is like Remember parabolas look like this. So like the h moves it right and left, opposite the way you think. The k moves it up and down. If a is negative, it reflects over the x-axis. If a is bigger than 1, it's a stretch, right? So very similar to that. This is the formula for exponentials. It just has a little different look to it. So y equals, usually we call the base a, so I'm going to call this coefficient b. So b times the base of a to the power of x minus h plus k. So that's the formula for exponentials for transformations. So the k value, as you might think, it's outside the kind of the base and exponent there. It's moving it up and down. The h is moving right and left, the opposite of the way you think. Kind of like that h moved it right and left, the opposite of the way you think. The b value does the same thing that that coefficient did there. If it's bigger than 1, it stretches. If it's negative, it reflects it over the x-axis. Right. So let's just talk about what would this one do here. So this one has a +2 outside. That looks a lot like a k value there. So it's going to move it up too. So I would move the asymptote up first too. So it was at y equals 0. Now the asymptote is at y equals 2. The point was at 0, 1. Now the point is at 0, 3. So I like to write the ordered pair where that point moves to. And on the left, the graph is approaching the asymptote and it hits that point and moves up really quickly. It's growing quite fast. Okay, let's try the next one. Again, start with your parent graph. So I'm just going to do 4 to the x. Again, 4 to the x looks a lot like 2 to the x. Just goes a touch faster. So y equals 0. Goes through the point 0, 1. Behavior on the left, approaches the asymptote, moves up pretty fast. That's the parent graph. So now which direction will the +2 move it? Well, that looks like it's up here in the exponent spot. And it goes the opposite way you think. So this is actually going to move it because it's x minus h. It's going to move it to the left. So everything moves. Moving the asymptote doesn't change it. So y equals 0. But that point at 0, 1 will now be at -2, 1. And the behavior hits this and goes up pretty fast. And you got it. This one, probably the hardest transformation of this type, or at least one of the trickiest, is when you have a different, I guess we call that a b value, the coefficient's a little different there. So y equals 0 is the parent graph, goes through the point 0, 1. And the behavior graph on the left approaches that, so it hits the point and moves up pretty quick. In fact, even quicker than 2 to the x does. It's 4 to the x. Okay, so we're going to take this and stretch it vertically. It might help to actually, this may seem weird, but I'm going to write write that ordered pair. Just it'll help you do a step here. So 0, 1. Remember when you write out all the ordered pairs of that function? Remember, there's only one ordered pair we're necessarily following here for our sketch. So that's the point I'm concerned about. And remember what the step was? If you had a coefficient in front, like 2, you multiplied the y values by that. That stretched it out, right? Same thing with negative. It would automatically reflect it. So to handle both of those transformations, I just multiply that y value by 2, and you get 2. Multiply this y value by 2, and it stays the same. It's still 0, if that makes sense. 0 times 2 is 0. So the asymptote is still at 0, y equals 0. But the point that we're following is at 0, 2. So this graph is moving up even faster. Still on the left, it's approaching the asymptote, but it's moving up faster. And actually hits the y-axis sooner than the other one did. So this is y equals 0. Goes to the point 0, 1. This is the parent graph I'm talking about. So I always do that dotted to start with, okay, as you're kind of learning this. Okay, so the negative in front just reflects it. Again, you could look at the ordered pair of that first point, 0, 1. All the y values are being multiplied by -1. So now this is going to be 0, -1. Or it just flips over the x-axis if you want to think about it that way. So now instead of growing, it's actually going down really fast once it hits that point. On the left, it's still approaching the asymptote. This one's kind of a different kind of transformation than the last one. It's in some ways similar, I guess. So it goes through 0, 1, something like that. Okay, so this one is going to be a reflection, but not over the x-axis. The negative is not in front of the function. It's attached to the x. So this is going to reflect over the y-axis. So unlike most of when the negative is in front, this is over the y-axis, not the x-axis. So this is the y-axis, right? So if you reflect over that, you fold over it. So instead of like on the right, it's going to kind of do this on the left, right? That's a reflection of the right-hand side. On the right, it's going to do what the graph is doing there, so it's going to approach the asymptote. So this is going to be exponential decay rather than exponential growth when there's a negative or reflection over the y-axis from the original parent graph. So this is y equals 0. Wow, this is doing both transformations, so this will take a second to do. So let's do one of them first. We just did reflection over the y, so let's do that. So let's do that one first, I guess. So that graph would look like this. We just did it. I did it dotted because that's not the final graph. So then the final graph, we're going to take that and reflect it over the x-axis. So that graph reflects here, so it's going to do this kind of weird looking graph. So that's the graph, the final graph. It's just a double reflection, reflect over the x and reflect over the y. So we've got this is kind of a longer lesson here. So we've got when it's 1/2. I think we already did this, didn't we? Yeah, 1/2 to the x. We already did that parent graph, so I don't need to do that again. So let's take that parent graph though. So y equals 0. Again, this is exponential decay, right? When it's 1/2. So it's going down, and it goes to that point 0, 1. Okay, so this one is going to be you're moving down 3 units because that's after, it's not in the exponent spot. That's not moving right or left. So the asymptote I would move first. So it's going to be y equals -3. The point goes down 1, 2, 3. It's now at 0, comma, -2. And the graph is decaying, going down instead of increasing. So again, we're just starting with a different parent graph. So you have to remember which parent you're looking at. Is it decay or growth here? So y equals 0. So it goes to that point, it decays, it goes down, something like that roughly. So this graph is going to move to the right 2 units, opposite what you think, x minus h, so h is 2. So that's going to move to the point 2, comma 1, and it is decaying on the right. It's approaching the asymptote. I think you're probably getting this. I just want to do one more of this one, and then we'll finish off on one more concept. So again, start with the parent graph. Don't forget to label the asymptote. I almost did. Y equals 0 is decay. Is our parent graph. So the 3, we're multiplying the y value. So it was at 0, 1. Now it's going to be at 0, 3 because the y value is multiplied and it's still decaying and it still approaches the asymptote at y equals 0. So it didn't move up, it just stretched. So it's falling faster, I guess. Okay, last question. It kind of gives us the form of the problem. And by the way, when it says f of x, I'm going to write it this way. Y equals a to the x, because f of x is y. I think it'd be easier in this case to write it as that. So we have some points. We can tell this looks exponential. It looks like exponential growth. I know a is bigger than 1 because it's growing. What you want to do for this is just plug in a point. Don't plug in this point, though, because every exponential, 2 to the x, 3 to the x, 4 to the x have 0, 1. So you really want to choose this point to plug in. It's a unique point. So it'd be y equals 4 A I don't know, and x is 1, so solve that. Well, it's pretty much already solved. A equals 4. So my equation would be f of x. You just got to plug that a into the function, right? Equals 4 to the x. That's going to generate both, go through the 0.01 and the 0.14. And that's how you do that kind of problem. Let's try a little tougher one version of that. So same thing, don't plug in 0, 1, let's plug in this one. So y is like g of x, so 9 equals a to the negative 2. This is a little tougher. So 9 equals, I hope you know that's a reciprocal function, that's 1 over a squared. To solve that, I would multiply both sides by a squared. And you get 9a squared equals 1, so divide by 9, and a squared equals 1/9. Square root both sides. Don't forget plus or minus, but in this case, you really only need positive. I know that it's not being reflected, so this is just a is a fraction, it's a positive fraction because it's regular decay. So my equation would be g of x equals a is 1/3, right? So 1/3, I would put that in parentheses to the x, and that'd be your final answer as far as the function would be concerned. Sorry for the long screencast, but that's the end of the lesson. Thanks.